So we said this is the Exergy balance for a closed system, right? Any Exergy change between two states of a system is because of either Exergy is transferring along with heat and work, or because of Exergy being destroyed. Okay, so uh, let's start by evaluating all the terms in this equation one by one. We'll start with the
Doctor,
yes.
how can the Exergy be destroyed?
Okay. Exergy destroyed is sort of an indication of the fact that you're destroying some potential of the system, right? We'll talk about that in a bit. So just be patient, but we'll come back to that. I'm happy you're excited to understand why Exergy is being destroyed, because that's one of the most crucial parts here. So let's start with the first thing here, Exergy change. Okay. So Exergy change between any two states of a given system can be very easily calculated once you have the appropriate properties to define the state. Okay, so uh, once you know the pressure and temperature for the two states, state one and state two, and also the environment is defined in terms of the pressure and temperature, P naught and T naught, then the exergy change between these two states is simply equal to this formula, right? I mean, this is basically what's coming from the formula for exergy. Okay, it's equivalent to the differences in internal energies, volumes, entropies, and then the kinetic energy and potential energy change. Now, usually these two changes are zero for most thermal systems because we don't have, we don't have any changes in kinetic or potential energy for thermal systems that we consider. For example, uh, a power plant, it's not moving anywhere, right? So this is how you calculate the first term, which is the exergy change between any two states. Now, the interesting part is how did that change happen, right? Or what are the things that contribute to that change? So there are three things that contribute to that change. The first is the exergy transferred that accompanies heat transfer. Okay, and that is basically this part right here. EQ indicates the exergy transfer accompanying heat transfer, and it's given by this formula. Okay, now here T naught and TB are both temperatures in degree Kelvin, so you got to make sure that you use that, not in degree Celsius. And this is under an integral. Okay, so T naught is the temperature of the environment. It will be constant. TB is the temperature of the boundary where the heat transfer is occurring. Now TB may be may vary with the amount of heat that's getting transferred, right? So that's why TB and delta Q both are within the integral. All right. We will see an example where TB is constant, and then we will be able to evaluate this integral in a rather easy manner. We'll talk about that later, but this is what you need to remember, right? This is what's in the integral, and this actually tells you how much is the exergy that gets transferred. Okay, and if you're adding heat to the system, certainly its potential to do work will increase, and therefore this term right here, EQ, will be positive. Okay, so this is the first part. Exergy transfer certainly increases the exergy of the system, right? Or it reaches a state with a higher exergy. Now, the second part is the exergy transfer accompanying work, right, given by EW. So this consists of two different components. One is the work actually done by the system, okay, and minus P naught V2 minus V1. P naught is the pressure of the environment, and V2 and V1 are the volume change of the system that you're considering, right? So between the two states. Here, as you can note, there is a negative sign in front of the work done, and this makes sense because if you're actually doing some work, if the system is doing some work, then we're going to lose some exergy, right? So the greater the work done between state one and state two, during in the duration between state one to state two, then the greater would be the exergy lost, right? So heat would add exergy, work would reduce exergy a bit, and then we have the last term, which is exergy destruction. Okay, the question is how is it happening, and well, why is exergy being destroyed? So I'm going to answer both of those questions, but the exergy destruction is among the most important terms in this whole chapter. Okay, it is. I mean, it's one of the reasons why we do exergy analysis, to figure out where exergy is being destroyed. And Most of the times you're interested to calculate exergy destruction and calculate exergetic efficiencies, right? Because as we have mentioned before, if less exergy is destroyed, it makes the system more reversible. Now, coming back to the question of can exergy be destroyed or why is exergy being destroyed? Well, as we said, exergy and entropy are quantities which are not conserved, right? So whenever a system is going through an irreversible process, there is some amount of energy that just goes into that process, right? Whether it's friction or heat transfer over a finite temperature difference or something, you lose some energy to that. There is some energy that's lost in the irreversible process. So the energy that's lost or the exergy that's lost during the irreversible process is what's what we call as the exergy destruction. All right, and the exergy destruction can also be written as T naught times sigma, where T naught is the temperature of the environment, again in Kelvin, and sigma is the entropy generation. Okay, and this is the entropy generation that you can calculate from entropy balance. And we already solved the problem on entropy balance. All right. So since the entropy generation, since the exergy destruction depends on entropy generation, it follows the same sign as entropy generation. So if you recall, when we are dealing with a reversible process, okay, whether it's internally reversible or totally reversible, whenever you have a reversible process, entropy generation is zero. All right, and if entropy generation is zero, exergy destruction is also zero. So this is the maximum work that you can extract, right, when you're dealing with a reversible process. And the value, therefore, at that state is basically what's the exergy. Now, on the other hand, if you're dealing with a process which is irreversible, then we know that there will always be some entropy being generated, right? Entropy generation will be greater than zero. And because here the only other term is T naught, and T naught is always positive or zero, so the exergy destruction will also be positive when there are irreversibilities within the system. And of course, entropy generation cannot be negative for any process that's possible. So same is the case with exergy destruction. So it follows the same signs. All right. So
Doctor,
yes, go ahead.
sorry for interrupting, but exergy is the useful energy, yes?
Yes.
So if it is like this and considered to be an energy, I really didn't understand how is it going to be destructed,
Okay.
because this will violate the conservation of energy. So
Yes. So we're not saying that the energy is being destructed. We are saying exergy is being destructed. And the reason we are saying exergy is being destructed is because some energy transfer is happening to things which we do not want to happen, right? So as a very simple example, if you're talking about expansion within a turbine, okay? So as the fluid expands within the turbine, there is some friction associated with the expansion process, right? So when you look at the enthalpies at the inlet and the exit, you will find that some part of the energy, some part of the enthalpy that it had, or some part of the energy it had, has been used to take care of has been lost in fighting the friction or in the friction process and overcoming the friction process. The rest is what comes, and some part of it was used to certainly provide work, and then the rest comes out as the fluid then comes out at a lower enthalpy S2. So from an energy perspective, energy is not being destroyed. It's just being energy is being lost to friction, right? But from an exergy perspective, the exergy that we had at state one, okay, which would represent the maximum work that you could extract, is some part of it is being destroyed as it goes through the expansion process, right? Because the work that you get in an actual turbine is less than is less than the work that you would get in a reversible process, okay? And that's simply because some part of the exergy is destroyed, or some part of the potential to do work is destroyed because it's lost in overcoming undesirable effects such as friction and other irreversibilities. So from an energy perspective, no, energy is not being destroyed. Energy is simply transferred to a quantity which you don't like. Okay, and so that's the whole concept of exergy destruction.